Okay, great. So thank you for having me here to talk today about the work that we've been doing in machine learning and mathematics. So as a brief introduction, I came to Trinity in 2010. No. Oh God, I can't even remember when I did. Yeah, 2010. Came to Trinity to do my PhD in machine learning. And I was a Gates Scholar and external research scholar while I was there. And at the time, this was a bit before the big machine learning boom that came kind of during my PhD, when the first big results on ImageNet, this kind of image prediction task, really started improving a lot. And over the next 10 years, we've seen machine learning become a kind of very hot topic in both industry and in academia. So when I finished my PhD, I left. I went to Google for 2 years, where I worked in research there, consulting with product teams to try and help them put machine learning into their products, and also doing a lot of teaching, because when I turned up, Google was transitioning towards being an AI-first company. And so they needed a lot of teaching for the engineers to understand machine learning, the kind of basics, and get that up to speed. So I ended up doing a lot of teaching, including in the Japan office for a couple of weeks, which was very enjoyable. And after those 2 years, I moved back to London. I started working at DeepMind about 4 years ago. And for most of that, I've been working on this intersection of machine learning and mathematics, and trying to answer the question of whether or not tools in machine learning can be helpful for making genuine breakthroughs in mathematics. And so this is what I'll talk about today. Go there. So the work that I'll describe, we published at the end of last year in December, and we framed this as using machine learning to guide the intuition of mathematicians to help them make discoveries that they otherwise hadn't yet found, or they otherwise might not have found without this technique. And what was really important to us was trying to make sure that we got to results that were not, rediscovering known results or kind of making small improvements, but genuinely finding new connections and patterns that mathematicians would look at as valuable, independent of the use of machine learning. And so we had these kind of comments here, which I think were really positive, and the kind of thing that we were looking for.
I can't see your presentation yet.
Oh, you can't see the presentation?
Yeah, I cannot see it. Maybe somebody else can. Can
others see it? It says I'm sharing my screen, but I don't know.
I can see it.
Sorry?
I can see it.
You can see it. Okay, then.
Yeah. I also see.
Yeah. Then it's the problem. I've set up my screen probably.
Yeah, it must be the screen setting, because I can see it as well. Yeah.
Okay. Now I can see it. Yeah. It was my screen setting. Yeah, I'm sorry.
Okay, no worries.
No worries.
Yeah, in order to do this work, we collaborated with some top-tier mathematicians, some of the best in the world, in 2 areas of maths. So we looked in knot theory, which is a subfield of topology, and representation theory, which is a subfield of algebra. And so in knot theory, we worked with Mark and Andrash, who are both professors at Oxford, although Mark did his, I believe, undergrad at Trinity in maths. And then Geordie Williamson, who is at the University of Sydney. And so these are the 2 papers that we also put out alongside the Nature paper, which were just focused on the mathematics. And so the kind of inspiration for this work came in part from Demis saying, putting forward this example of Ramanujan. And so Ramanujan was a very famous mathematician, and he was famous particularly for being a very intuitive mathematician. So he would see patterns that other people couldn't see, and they would.
It was a Trinity, of course, you may mention.
Yeah, that's actually, I didn't realize that, but
he is.
Yeah,
have you seen there's a movie about him, which you can buy on a DVD from Amazon? Sorry?
The Man Who Knew Infinity, I think, was the movie.
Exactly. Yeah, there's a book and then there's a movie now. And that is completely focused on Trinity, this movie.
Oh, yeah, no, that's a really good point. That never occurred to me. I didn't realize how heavily Trinity was represented in these slides.
Oh, I think Trinity kind of discovered him, you know. They brought him from India to Cambridge. So I don't know how his work would have continued if he would have stayed in India.
Yeah, well, I mean, it was obviously a really great thing for, you know, at least Western or the recording of mathematics that he was discovered and that his abilities were discovered, especially because he didn't have as much training in formal proofs as other mathematicians did. But yes, he had this kind of ability to just see these patterns that other people didn't see. And so there's a sense that there's this kind of intuitive part of mathematics, which is different from the theorem proving, but it's kind of seeing things which may be true that you can then ultimately go on and prove. And so I'll just put a couple of examples here of how this process is kind of a common way that mathematics is done. It's not the only way, but it's a good way. It's a good way to think about how some of mathematics is done, is that conjectures come about because mathematicians get an understanding of particular mathematical objects that they care about by looking at examples of them. So they see examples of these mathematical objects, they get an intuition for them, and they can detect patterns that are occurring in these objects that they care about. And once they do that, they can formalize these as conjectures of things that they think might be true. And then once you have a conjecture, you can go about proving it. And if you go back, even before the existence of computers, there's early examples of things like the prime number theorem, which is a very clear example because people used to spend years writing out tables of prime numbers by hand so that they could actually see what the prime numbers were. And then once they had this list of prime numbers, they could look for patterns in it, and then they could put forward a conjecture like the prime number theorem. And so this is manually writing out examples and manually finding the patterns. Once we had computers, we started to compute examples, and Birch and Swinnert and Dyer did their work at Cambridge, and that was, I don't know what college they were at, but they kind of formulated one of the most famous conjectures in the world today. So the Birch and Swinnert and Dyer conjecture is one of the Millennium Prizes, which you're probably familiar with, the kind of 6 biggest open problems in mathematics. And in that case, they used computers to generate the examples. They looked at the examples and then manually detected this pattern by seeing that it had this form that you can see on the plot. And so what we were doing here is taking the next natural step, which was nowadays it's very easy to compute very large data sets of examples of mathematical objects. And they can be so large and the objects can be so complicated that it's no longer easy for mathematicians to look at the data and be able to see the patterns themselves. And so what we're doing in this work is we're using machine learning to computationally detect the patterns and then help the mathematician understand what these patterns are so they can formulate a conjecture. So this is the way that we did this work was this kind of back and forth process between the mathematician and then the computer or the machine learning, where it opens up a new kind of question that mathematicians can ask for a computer to automatically do for them, which really accelerates the process of mathematics and gives them ideas that are different than what they might have otherwise expected. So you get these kind of surprising and interesting results. And we do this by using 2 main techniques for machine learning, which I'll just describe in the next number of slides. And those are what I would call supervised learning and attribution. So supervised learning is the problem of finding a function f such that this function approximately maps x to y for a large data set of x and y pairs. So this is traditionally in statistics called regression. but we might be doing regression or classification or a number of different things, but just generally we're looking for a function that maps between two pairs of objects. And then attribution is once we have a learned function, can we identify parts of the input that a particular model finds relevant for predicting y? So once you've got a trained function, we might want to understand which parts of the input are being used to make the prediction of y in this function. And so I'll give some examples to make that a little bit more clear. A great example, canonical example in computer vision machine learning is recognizing cats in images. So this is an image of a cat. And if you were to run a trained machine learning model on this cat, a supervised learning model that's been shown lots of examples of images and the labels of what's in the image, then you get an output that looks something like this. It would have a number of different classes of what could be in the image, and then a probability associated with the fact that that's the class of the image. So this would be the top 5 classes. And so it's most likely that this is a tabby cat. And so we would just probably make the prediction that this is a tabby cat. And so this is what a trained supervised model would do. We have some function that maps from images to an element of a finite set of classes. And so if we were then going to look at attribution on this particular function that we've learned, this function that maps from images to classes, we would ask the question of what parts of the image, so what parts of the input X, which in this case we could say is the pixels, so the image is made up of lots of pixels that the function looks at. We'd say which pixels is the function using in order to make that prediction that it's a cat. And there's a number of different ways to do this, but the one that we focus on and the one that I've shown as an example here is pretty mathematically simple, which makes it quite nice. And that's just taking the derivative of the prediction with respect to the input pixels, and then looking at the pixels that have a large derivative. And what that is essentially saying is, for any given pixel locally, if I change it, how much will it change my prediction of what the object is? And if you do that here and kind of only focus in on the high value pixels, you can see it's in fact, looking at the cat. So let's look at a kind of trivial example of how we could use these two techniques to rediscover an existing formula in mathematics. So a simple formula is Euler's formula. And what question we might be asking in rediscovering this is whether we can tell how many edges a polyhedron has by only looking at other measurements of this polyhedron. And so in order to do that, we have these fundamental objects, these polyhedron, and we can compute a lot of measurements of these. These are all relatively simple measurements. So we can measure the faces, the vertices, the surface area, or the volume, as well as the edges. And we can use supervised learning once we have a data set like this to see if we can find a function which maps from the inputs, which in this case are the measurements on the left, to the number of edges. This would be the same as before, instead of going from images to classes, now we're going from a kind of vector in Rn to an integer. And we can see if the machine can spot a pattern here, if we can learn a pattern that maps these two spaces. And it turns out that you can. If you were to train a machine learning model on this, it would tell you that it can predict the edges perfectly from this information all the time. But then you could go a step further and use attribution to ask the model which parts of the input space were relevant for the function to make this prediction. Because at the outset, pretending we knew nothing, the first training of the model would tell us that the information necessary to know the edges is in the information on the left. And then if we use attribution, it would narrow this down further to say that actually all you need is the faces and the vertices. You don't need to know the surface area and you don't need to know the volume. And you may already know Euler's formula, but it is exactly edges is the faces plus the vertices minus 2. And so once you came down to just having the faces, the vertices, and the edges, then you could kind of look at these. Now that you know where you're looking, it's a lot easier to tell what the formula is, rather than if you're starting at a large number of measurements. And so what we ended up doing, the kind of process that we followed in working with mathematicians, looked a bit like this. So it was to say that what's important to begin with is to have the mathematician come with a hypothesis that looks like the one previously. So a hypothesis that there exists a function mapping from one representation of a mathematical object to another. And so they believe perhaps that one might exist, but they don't know. And so in order to help them understand whether such a function exists, we can generate data. So we can generate example pairs of the input and output representation. We can use machine learning models to train a supervised model in order to map a kind of approximate function to map between these two spaces. And this in itself is often very useful, just to let them know that there is potentially a function that they're looking for and for them to be thinking along that particular direction. But we can also go further. We can use attribution to narrow down which parts of the input are actually relevant for the thing that they care about. And so they can take this information and they can conjecture new candidate functions, reformulate the hypothesis or alter the sampling distribution, so what kind of objects that we're looking at, and ultimately, hopefully, get to proving a theorem of interest. So I'll maybe pause there and ask if anyone has any general questions before I go into the specific examples of how we use this in knot theory and representation theory and the results that we found. I think you're muted, Gerhard. But I'm also very happy to just continue. You also still.
Yeah,
now you're.
Yeah. So why don't you continue? I think if nobody raises his hand,
Perfect.
then you can stay in the flow of your thoughts.
Easy. Okay. So knot theory was the first area that we looked at, and I think gives a nice demonstration of how powerful this technique can be, even in the simpler side of the setup. So obviously this is joint work with Mark and Andras, and Nenad was also another DeepMinder on the paper that we published. So as a quick primer, a knot is a closed loop embedded in 3 dimensions. So this is a 3D spinning picture of a knot. And so it's kind of a line that follows itself around in 3-dimensional space and eventually comes back to the same point. And 2 knots are the same if there's a way that you can kind of smoothly deform the knot into its other representation. And so the knot theory is just the study of these different kinds of knots and different properties of those knots that we can look at to distinguish one kind of knot from the other. As you can imagine that if I had one of these in real life, and then I kind of twisted it around heaps and gave it back to you, it might be difficult for you to distinguish whether a knot that I've just given you is the same one as before. And so the way that knot theorists and topologists look at these objects in order to help distinguish them and understand them is looking at what are called knot invariants. And knot invariants broadly fall into a number of different classes. And there are 2 main classes of knot invariants that we'll refer to as geometric invariants and algebraic invariants. And so these are all fundamental measurements of something interesting about the knot, but they come from different areas of mathematics. So obviously geometry and algebra. because it turns out that there is a kind of important notion of geometry that's associated with a knot. And once you have that, you can measure its volume, you can measure kind of different lengths of parts of the knot, as well as many other measurements. And then for the algebra, what we're looking at are things that are more like the diagram on the left. So you have graphs associated with a diagram of the knot, and you can calculate properties of these graphs, or you have recurrence relations on knot diagrams, which give you polynomials or other things like this. And these are both very rich ways to understand knots, but because they come from very different areas of mathematics, there's not a lot known about direct connections between the two. So there was essentially previously no known direct connection between the algebra and the geometry, aside from through the original object itself, the knot. So we know that if you give me a knot, for example, a diagram like on the left, I could calculate its geometry and I can calculate its algebraic invariance. But we wanted to ask if there exists a relationship directly between these two. And this would be surprising, one, because there's one very famous conjecture called the volume conjecture, which says that the volume, which is a geometric invariant, is contained within the algebraic structure. But that's not been proven. And aside from that, even though topology is a fairly computational field and good computational tools have been around for a while, no other kind of proven patterns have been noticed. So concretely, if we looked at a kind of X and Y representation like we did before, for every knot, you can calculate its geometric invariance, and you can see an example of a couple of them here, and they tend to be real or complex numbers. And then on the right, you can see a couple of the algebraic invariants. So some of the most common ones are the signature and the Jones polynomial. And those algebraic invariants tend to be integers or polynomials with integer coefficients. And so the question is, can we predict something on the right from something on the left? And in particular, we trained a neural network to predict the signature from the geometric invariance. And it turned out that the signature can be very well predicted from the geometric structure. So there's this very kind of basic and fundamental algebraic invariant, probably the most fundamental and basic algebraic invariant, can be predicted from the geometry. Not perfectly, but very, very well. And so even at the outset, I think this was very surprising to Mark and Andras, and was something that they wouldn't have previously considered seriously. And so we could take this a step further, and we could use the attribution techniques that I mentioned before to see which part of the geometry is actually controlling this relationship. Because obviously there's quite a lot of the geometry, but it turns out if we look at this diagram that there's 3 measurements that are particularly relevant for making this prediction. And you can see that they all have a very similar name. So it's the imaginary part of the meridional translation, the longitudinal translation, and the real part of the meridional translation. And so those are actually all measurements of the same part of the geometry, which is called the cusp. So again, this was kind of very surprising and exciting to Mark and Andras. So this gave them something very concrete to go away and think about and look at, because now they know precisely which part of the geometry and which measurements are controlling the signature. And what they then realized was that there was a new measurement of the cusp geometry called which we call the natural slope, which is a small formula involving those 3 terms. And if you look at the natural slope, suddenly you have a quantity which is linearly related to the signature. Again, with some error bound, but very close, and in a way which is very surprising and holds out to even very large or knots with a very large signature. So this is a pretty obvious relationship, and we could empirically validate over many knots that it seemed like the relationship was linear with some kind of bound based on the volume of the knot, which is both visibly, it's easy to see, and also makes a lot of sense theoretically that this kind of relationship should be bounded by the size of the knot. So after looking at this conjecture for a while, we were able to construct a counterexample to this conjecture. So there is a very small family of knots for which this conjecture is not true. So we tested this knot for kind of the first millions of knots and also millions of very large random knots for which it holds. But we were able to find a very small class of counterexamples for which it doesn't. And this was important because what was required in the end was making use of a little bit more information. And if we look down this chart, you can see that there's both the imaginary part of the short geodesic and the injectivity radius were the next most salient features. And it turns out that involving either of these terms allows us to actually create a correct conjecture. So either a correction term that involves the short geodesics, the imaginary part, or the injectivity radius, which is very related. And so the theorem was essentially what we had stated before, but with an extra term based on the injectivity radius. And this was the form that Mark and Andros were able to prove. And so this then resulted in the first connection between the geometric and algebraic structure representation of knots. So hopefully that was a kind of pretty straightforward example of using this to discover a pattern that had gone unnoticed for, let's say, 40 or 50. Knot theory has been around for a long time, but we've had a largest data sets of knot invariance at least for the last 30 or so. And it's very interesting that the slopes formula is very simple. It's a very kind of, even as an outsider, you can see it's a very simple and natural quantity based on these other measurements of the geometry, but it's easy to overlook that this might be the one that people should be looking at without having something computational to detect that this pattern was there. And this is one of the really, I think, valuable things that machine learning can bring to the table, is that mathematicians often have a very refined intuition that they use to understand where they should be looking at mathematical problems, because you'd be totally lost without it. And occasionally there are kind of simple patterns that it seems like mathematicians would otherwise overlook, and all that they require is to be pointed in the right direction, say like, actually there is something interesting here, and suddenly, with a little bit of point on the map, they can do a lot of really interesting work. So the second area that we looked in was representation theory with Geordie Williamson and a number of other DeepMinders. And this is a caveat that this is a kind of overview of using this process together with Geordie to understand the objects that he cares about. And that a lot of the work in the end was coming to an understanding of each other's fields. I think it sounds like there's at least one person on the call who would understand, like, bridging different domains, like, I guess, mathematics, and in our case, more a kind of machine learning and engineering. There's a lot of communication that needs to happen in order to get to a common understanding of the problems and really make progress. And so a lot of the work was really us understanding representation theory and Geordie understanding machine learning. And once we were there, we could make some very surprising progress on a really fundamental problem in his area. So yeah, Geordie's really not good at drawing very nice pictures of these objects that we care about. And what these objects are based on are symmetry groups. So in particular, we look at the permutation groups. And a permutation is for a fixed collection of objects, like our A, B, C, D, E here. Permutation is something that swaps the order of these objects in a particular way. So illustrated in this slide is the permutation 3, 2, 4, 1, 5. And that's the permutation that takes the first object and puts it in the third slot. This keeps the second object in the second slot, takes the third object and puts it in the fourth, and so on. And you can see the arrows moving the objects into their new location. And so representation theory in part studies these groups of permutations. One of the actual objects that is kind of fundamental in representation theory is called the Coxeter group. And the permutation groups is one Coxeter group. And these Coxeter groups are defined by two different transformations, reflections and simple reflections. So for the 4-element permutation group, then there are 6 reflections, and the reflection is a permutation that swaps 2 objects, only 2 elements in the sequence. So 2, 1, 3, 4 swaps only 2 and 1 and keeps 3 and 4 in the same spot. 3, 2, 1, 4 swaps only 3 and 1 and keeps 2 and 4 in the same spot, and so on. So these are the 6 reflections that we would care about for S4. And then among these reflections, there's also things called simple reflections. And the simple reflections are the reflections that swap neighboring elements. So out of all of permutations, which can swap all of the elements in any order, we have the reflections which swap only 2 elements, and then the simple reflections swap only neighboring elements. So this is kind of building up to the objects that Geordie studies, one of them, which are called Bruja Graphs. And a Bruja graph is a way to take all of the elements of a permutation group and look at some of the structure of them based on their reflections and their simple reflections. And so I'll show you a picture of one soon, but we can construct this graph by making a node for every permutation. So every possible permutation we put in the graph as a node, and then we draw an edge between them if you can go from one to the other by a reflection. And we start at the bottom with the kind of identity permutation, so the one that doesn't change a sequence if you apply it to it. And then you start to generate new permutations by using the simple reflections, and then keep doing this. And every time you add a new element to the graph, you kind of go up a level. So what you end up with is a graph that looks like this. And you can see that on the bottom, you start with this permutation 1, 2, 3, 4, which is the simplest permutation. And then as we go up the graph, the solid lines are simple reflections. And as you perform a simple reflection, you go up a level and then you add a new node. And so we know the 3 simple reflections for 1, 2, 3, 4 are swapping 1 and 2, swapping 2 and 3, and swapping 3 and 4. And you can see those 3 at the next step up in the graph. And then if you take those 3 nodes and do the same thing to them, you'll start to generate new permutations. And if you generate one that's already been, you just ignore it and you don't use that. But you kind of keep doing that till you've generated all of the permutations, and then we add in dotted lines for any of the reflections which are present here, which are not simple. So that was a fairly in-depth kind of algorithm for coming up with this object, but it turns out that this is a very fundamental and interesting object if you want to understand what's going on in these groups. So once we have Bruja graphs, there's this kind of 40-year, 50-year, 40-year conjecture in representation theory, incredibly central, called the Combinatorial invariance conjecture. And what it says is that if you're given that graph in the previous slide, but without any of the labels on it, then you can calculate another quantity, which is called a Kashtan-Lutzig polynomial. And the Kashtan-Lutzig polynomial is the basis on which all of representation theory is built. It really tells you, they're very small, relatively speaking, so they're kind of polynomial with only a few terms usually, but they tell you something very deep and subtle about the nature of these groups that they study. Whereas on the other side, these Bruja intervals are huge. I showed you a very small one on the previous slide, but as you'll see, they get big very, very quickly. And they also capture the same kind of information. And so it's known that if you have this labeled graph, it's very easy to calculate the KL polynomial. But it's not obvious that if I give you this graph and not the labels, that you would be able to do the same thing. And so what they've been searching for a really long time is a function that maps from graphs to polynomials with integer coefficients. And it's kind of long believed this exists, but progress has been slow, in part because these graphs are so large that they're very hard to look at and reason about for a mathematician. And so up until we started this work, there was some understanding of what the first couple of coefficients of the polynomial mean, but no meaningful understanding of what happens later on in the polynomial, except in some kind of restricted cases. So the question that we're asking here is, on the left, we have these Bruja intervals, and on the right, we have an integer coefficient polynomial like the one on the right. And we're asking, is there a function that maps from one object to the other? And so what I was saying is that for most intervals that we can easily compute, the KL polynomials are very simple. So it might have a couple of terms. And so you don't really see anything interesting that's coming from that. This is the smallest graph that has a Q² term in it. So you could think of very reasonably that this one on the left is like the first interesting graph. And this is not even very small. Obviously, it's quite hard to look at this and see what's going on. And this is a kind of representation of that same graph. And if we go up just a little bit again and get just a slightly more complicated polynomial, the graph is now so complicated that no one can reasonably look at that and see what the structure is. It's too difficult to see. And these graphs are very densely connected in the middle, and they have this kind of structure. And there's no way to reasonably plot this to see what's going on. And this is still a very small example. Bigger examples are just entirely impossible to see. So what we could do is look at the algorithm for computing the KL polynomial from the labeled Bruja graph and try and take inspiration from this to see what kind of neural network, what kind of machine learning model might be able to look at the graph structure and try and make predictions of what the polynomial is. And I guess we won't go into that too much today, but the formula looks very much like a graph-based formula. So you can look at the values, you can calculate the values of KL polynomials at neighboring nodes and use those as you go down the graph in order to understand what would be happening at the different nodes. So in order to see whether this function exists, which is the fundamental question that mathematicians are asking, we can build a large data set of Bruja intervals. And then we can train the machine learning model and see whether or not it can predict the polynomial. And so to start with, our kind of first simplest model was able to predict the coefficients of the polynomial surprisingly well. So for example, for Q, you can predict it with 98% accuracy over a baseline of 21. And then 63% compared to 12% for Q², and so on, which is very encouraging. That's not getting it exactly right, but already this is much better than what one would naively expect, or the mathematicians would expect. There was, Geordie had spoken to other mathematicians who said that they were very skeptical that machine learning would be able to predict anything about the higher coefficients of KL polynomials from a Bruja interval. But once we've got this trained model, we can do something similar to before. So we can look at which parts of the input are responsible for the predictions of the polynomial. And in the cases of a graph, this ends up looking a bit like which nodes or which edges in the graph are contributing to the prediction. And by looking at a number of these, Geordie was able to make this observation that aligns with previous theory in around Bruja intervals, that there's a structure in these graphs called dihedral intervals that might be particularly relevant for predicting the KL polynomial. And so once we found this, we incorporated this into the way that we were making predictions, and suddenly we were able to predict very accurately what the actual value of the KL polynomial was. So this signaled that we were onto something correct in terms of the structure, in terms of what what should be necessary and what we need to be looking at to understand the KL polynomials. And this led to a second observation. So on the model, we were able to not just look at which edges, I guess what nodes and edges were present for particular examples, but across the whole data set, we can look at which reflections are on the edges that were relevant for predictions. So we know that all of the edges are a reflection. So you can describe them by the two spots that they swap. And this information isn't made available to the machine learning network. So it's just taking the plain graph, but we know, since we generated the data, which reflection that the edge corresponds to. And so we can plot these for the relevant edges and nodes in the graph and see which reflections was the network paying attention to, even though it didn't know which ones that those edges were. And it turns out it heavily overrepresents what are called extremal reflections, which are reflections that involve either the first slot or the last slot. And so this also was very surprising. No one had previously identified this relevance of the extremal reflections to the task. But it turns out that this was one of the fundamental observations that led to our ultimate result. And so what Geordie was able to do with this understanding was discover this decomposition of the graph into what we called a hypercube decomposition, which is made up of if you know the extremal edges, the graph kind of breaks up naturally into these two pieces. And if you have these two pieces, then there is an algorithm that doesn't use the labels, which is able to calculate the KL polynomial. So this in itself was already a huge result, although it doesn't resolve the conjecture, because in order to make this decomposition, you still need to know which ones are the extremal edges, which is a lot less information than the full labeling, but it's still using information from the labeling, which we're not allowed to do. But the really interesting result that we came to further was that it looks like all hypercube decompositions give you the correct answer. So the real key was understanding that this structure exists and that there is a canonical hypercube decomposition that is given by the extremal reflections. And if you know that, you have an algorithm for the KL polynomial. But it turns out that any hypercube decomposition that looks like this would give you the correct answer. And we verified this computationally up to a very large number of symmetric groups. And while we can't say for certain that the algorithm is actually correct, there might well be a counterexample living in a very high symmetric group. It seems very plausible, and the structure is very instructive. So even if it was the case that a counterexample existed, that itself would be interesting because it would be saying something new about why this doesn't actually work all of the time. And that is the end of the slides for today. So those are the two examples of what we found, and we've been really pleased with the reception by mathematicians generally, as you know, both the ones that we worked with who found that the process was an interesting and enjoyable process, which I think is important for mathematicians. This has got to be something that they actually want to use and they think it gets them to results that are interesting for them. And also from the mathematical community in general, who I think have traditionally been skeptical of how useful machine learning can be in their fields for good reason. I think this is a good first step to show that very interesting, surprising results that are mathematically valuable can come out from using these tools in even relatively limited ways. So that's, I think we nailed that at about 11 o'clock. So I'll just kind of leave it open for any questions that you might have.
Yeah, thank you very much, Alexander. This was very, very fantastic, fantastic talk. And we also, DeepMind has come and made enormous impact. Also, I think the protein folding work. So I'm trying to set up a, if it's possible, like a similar event on the protein folding work later.
Mm-hmm.
Because we had a lot of very important protein work is also done in Cambridge and Trinity. Maybe Fukumoto-sensei, if you, as mathematician, maybe you can ask the first question. Fukumoto-sensei, hello. Maybe I should also say here, everybody, if you don't know, there's the Nature front page was devoted to Alexander's work, I think in December last year.
Yeah.
Yes, this is very curious, and but I want to know how non-expert could reach this kind of conjectures. For instance, volume conjecture relates hyperbolic geometric volume and I think algebraic knot properties. And I think the human should have some knowledge, and then there is a few entities that may or may not have relations, and then before putting this into machine learning or AI, I think you have some preliminary conjectures. Mm-hmm. Without such conjectures, can you get some meaningful results?
Yeah, so let me just check that I have your question correctly, but I think I do. So you're saying for finding, you know, this kind of conjecture, this relationship, there's this initial mathematician, like the mathematician is really bringing this initial hypothesis, and you know, can the system do anything if you don't have this there? And I would say absolutely not. And I should go into a kind of detail that when we were doing the work together, there's a lot of kind of mathematical knowledge which is coming into identifying that this is the right thing to be looking for. So it's very much not the case that you could just calculate lots and lots of invariance for an object and then apply this technique to find where the relationships are, because one thing that would probably happen is you find a lot of relationships that are obvious, or things that mathematicians know would happen and they understand well. And so really, there's a lot of the human expertise goes into asking the right question. And the fact that we could kind of relatively easily get something interesting here was because Mark and Andras came up with this question. They knew that if there was any relationship between the geometry and the algebra, it would be interesting. And actually, when we trained these models, there was a number of different parts of the algebra that we could predict reasonably well. So it wasn't just the signature. But when we talked to Mark and Andras, they were like, well, the thing that we should focus on is the signature. For a number of mathematical reasons. They're just like, it kind of made sense to them. It's a simpler, or it's a more fundamental invariant that it's more likely that they would be able to prove something about, which is really important. So for some of the other invariants, they said, well, it's really interesting, but it's unclear how someone would go about proving that. So we should really focus on things that we can prove and that kind of feel to them to have a good connection. And so there was a choice there by them as well to focus on that. And that maybe not so obvious from the story, but was a constant presence. So we were kind of giving ideas to the mathematicians, but they were really taking this, and it was really guiding them rather than the other way around.
I think there are several versions of Volume conjectures, but I think you discovered much deeper relations.
Mm-hmm.
This is never expected previously.
Yeah, that's exactly right. So I'm sure for the volume conjecture, I'm sure nobody expected that before somebody found it. But here, yeah, nobody that I am aware of really expected that there was any relations here, or that, yeah, if there was, they would have noticed them before. And so this was why this was so exciting. When we asked Mark and Andras, this was the first place that we looked, and they said, well, you know, there's a hint that there's something there, but they're like, if you could find anything, that would be really exciting. Almost certainly you won't. Like there couldn't be a connection between the geometry and the algebra, but, you know, have a look. And then we did, and there was something there.
Then do you have your own algorithm how to cook up using? This is secret, your secret to use.
No, it's no secret. It's like very standard kind of machine learning techniques. So for this prediction, there's some code that we released that trains the model to do this, and it's really simple. It's like 20 lines of code, and if you thought to give this to anyone who knows machine learning, they would be able to find it even without the code very easily.
Thank you.
I think you're muted, Gerhard, if you're trying to talk.
I'm sorry, I always forget this. I'm sorry. Professor Mizuguchi, do you like to ask a question next, because you are also a mathematician? So,
Oh, thank you very much. Thank you very much for your nice talk. And I can imagine the machine learning algorithm for the numbers, but you are considering the knot or structure graph or structures. Is there a general representation for the structured object in mathematics?
Yeah, that's an excellent question. So yeah, we kind of took an easy representation of knots by taking their invariants, which are just kind of, we can think of as real vectors, which is something machine learning is quite good at. And for representation theory, it was a little bit more of a complicated representation. It was a graph, but it's also something which is fairly well studied in computer science, right? Like we look at graphs for a lot of problems. I think you raise a more interesting question is like, okay, what if we wanted to reason about the knot directly and take some kind of representation of this object, which is true to the kind of, to the underlying object? And the answer is that there's no standard way of doing this at the moment. I think one of the interesting research areas in machine learning is trying to come up with new neural networks or new techniques that are good good for learning functions from structured objects. But we hadn't looked too far down that path, and no one has done this for knots that I'm aware of. You could look at more general architectures that say look at a specification of a diagram, so looking at a planar diagram code, a PD code, or looking at a kind of, you could think of a graph that represents a knot, like the kind of black and white graph, but it's a wide open and really interesting question, actually. And I think this is one of the reasons that some of the people in DeepMind and who are more on the machine learning side find mathematics really interesting, is because in some sense, for other applications, we ran out of interesting structured objects. You know, we had images, which are kind of grids of points, and then we have sequences, and then they're like, well, we'd like to model something more interesting, but it's not clear what there is. And I think maths has a bunch of really interesting objects which have interesting symmetries and interesting structure that we could really try and make networks that we're good at understanding.
Thank you very much. So for the graph structure, so it is easy to considering the matrix representation, but to get efficient some knowledges, you may use other hidden structure or something.
Yeah, so for the graphs, you could the kind of networks that we have, you could look at the matrix structure and use that to implement the function that we care about. So I can describe what the network actually does in this case. So in the case of the like the simpler example of the invariance, a neural network will just take all of those invariances as an input, and then you kind of perform a linear transformation on them, and then for every coordinate of that linear transformation, you apply some nonlinear, kind of an element-wise nonlinear function, and you just do that a bunch of times. For the graph, you do something similar, but on the graph structure. So you start with a small vector at each node in the graph, and then you do that same process I described on each element of the graph, on each node, and you kind of go through and calculate a new vector in RM, and then you take those vectors and you pass them along the edges. And so you say any node can look at all of the vectors for its neighbors, and you take all of them and then you average them or you aggregate them in some way. And then at the second step, you take that averaged vector, you run it through a neural network again to make a new kind of latent vector. And then you perform this message passing process. So you have lots of neural networks all throughout the graph. And then in order to start learning about the neighborhood of the graph that you're in, you keep doing this parsing and aggregation. And then at the very end, you look across all of the whole graph and then use the latent representation of the whole graph to make the predictions of the individual terms. Hopefully that it's a bit hard without a whiteboard, but hopefully that kind of made sense.
Thank you very much. Very interesting. I'd like to learn too much. Thank you.
Thank you.
Okay, thank you. If anybody else has questions here, anybody else has questions? I think, okay. Thank you so very much, Alexander, for this fantastic event, and congratulations to your great work. I'll send you an email, and I will try to ask if there's a possibility to have a similar event on the protein folding work, which is also very interesting and important. And it's interesting that you spend time here in Japan. If I had known about you, you could have joined our dinner meetings here. When was that?
That was a long time ago, I guess. That was probably six years ago.
I started Trinity Japan about 8 years ago, so we were already doing these events.
Okay.
So
well, I'll go next time if I have an excuse to go to the Japan office, which hopefully I will again one day.
It would be fantastic. Yes, if you tell me in advance, I can set up our dinner meeting so that it fits into your schedule. Also, if you have other Trinity friends, please send them along. Tell them about us. Okay, thank you so very much. I think you are on your way to your next meeting now.
Yeah.
So thank you very much for this fantastic presentation and very fundamentally important.
Thank you very much. Thank you for hosting me and having the chance to present this to the Trinity and friends that we have here. So thank you, Fukumoto Sensei and Mizoguchi Sensei.
Thank you so much.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.